Let's go through the basics of valence shell electron pair repulsion, or VSEPR. The idea here is that if you take a look at the central atom and you look at the groups of electrons around the central atom, due to the repulsion of the groups of electrons, you can use that repulsion to determine the shape of the molecule or predict the shape of the molecule. So for instance here we have BeH2, which the dot structure you would find would look like this. Now, when we do the dot structure, it really doesn't matter or tell us anything about the geometry of it when we draw it. However, in this case, we've got two groupings around the beryllium. There's the bonding pair to one hydrogen and the bonding pair to the other hydrogen. When you have two things that are repelling each other around one thing, you end up with a shape kind of like this. Notice that if we were to measure the angle here, this would be 180 degrees, and we would call this a linear molecule. At this point, if we were to add in the elements, then we would say that there would be beryllium, hydrogen, hydrogen, and the angle between those bonds would be 180 degrees. Here we have BH3. Notice that the boron has 3 electron domains around it, the 3 bonds to the hydrogens. So 3 electron domains spread out as far apart as they can from each other would make this type of shape. So if I were going to do this for the molecule there, I would have a boron, hydrogen, hydrogen, hydrogen. In this case, the bond angle between those would be 120 degrees, or 1/3 of 360. Next we have methane, and if you look at the carbon, the central atom here, there are actually 4 groups of electrons around the carbon, each of the 4 bonding pairs to the hydrogens. 4 pairs around any one thing. This one's a little tricky, but it's going to make what's called a tetrahedron. Now, drawing this is a little tricky as well. Usually what we do is we try to draw the carbon. We're going to draw 2 of the hydrogens in the plane of the board. And what we're going to try to do is add a little bit of perspective here. We're going to have 1 bond coming out of the plane of the board, bonding to a hydrogen. And that's shown with the dashed lines coming out of the board. And 1 bond going back into the board, into the plane of the board, or behind the board. That would be shown as a solid wedge. So this gives you kind of the perspective of the 3-dimensional shape. The other thing that's tricky with the tetrahedral is the angles aren't quite so obvious. The angle here is going to end up being 109.5 degrees. And then this angle will be rather important when we start dealing with larger biological molecules. So you should know that number. Now for some practice. So you can follow along on the sheet that you have for using the VSEPR steps to determine the 3-dimensional structure. The first step is to do the Lewis dot diagram. So you've got to flip the page over and do all the steps on the other side first. So if we do a count of all the electrons, we have 1 atom of carbon, which is 4 electrons. We have 2 atoms of hydrogen, which would be 2 electrons. And we have 1 atom of oxygen, which would give us 6 electrons. So total, we have 12 electrons to work with. Now, this seems a little bit different than the ones we've done so far, because we actually have 3 different types of atoms here. You're going to find that oftentimes carbon is our central atom. So I'm going to go ahead and draw carbon here, and I'm going to put the other elements around it. like this. And then we're going to go through our Lewis dot diagram rules. We have a pair of electrons for each bond. And then we're going to do the good host rule. We're going to put electrons around the atoms connected to the central atom, make them stable first. Of course, hydrogen only needs the 2. So we've made oxygen more stable. Now we're going to check and see if we have any electrons left over. And we have actually used up all of our electrons. Problem here, carbon doesn't have an octet. So we're going to get rid of those 2 electrons on the oxygen, and we're going to share those with the carbon, creating a double bond between the carbon and the oxygen. So we now have our Lewis dot diagram for this molecule. Step 2. We're going to count the number of electron pairs around the central atom in your dot diagram. Note, if there are multiple bonds to the central atom, each double or triple bond counts as if it were a single pair of electrons, even though more than one pair of electrons is actually being shared between the 2 atoms in question. So given that, I would count up 1, 2, 3 electron domains around the central carbon atom. Now, 3 electron domains, I'm going to go ahead and write that out here. I have 3 electron domains. And this is a logic thing. You need to include that in your explanation. 3 electron domains tells you that you're going to have, let's go back and check that out. 3 things around the central atom is our trigonal planar. Let's write that out here. So that's our trigonal planar shape. We're going to go ahead and draw that then for this molecule. So we'll put carbon here, and it doesn't really matter where we put things. Kind of like to be a little symmetrical. So I'm going to put the double bond O over here, and then the hydrogens here and here. Our bond angle, 120 degrees, and we would call this trigonal planar. Of course, by accident, I got ahead of myself here. I actually did step number 3. So use the number of electron pairs obtained in rule step number 2 to predict a preliminary shape for the molecule or polyatomic ion. In doing this, we ask ourselves, what shape would 3 electron domains have? And then, of course, we end up with our trigonal planar shape here. Right. Now, we say preliminary because if there happen to be any lone pairs around the central atom, which we'll get to in the next example, we would need to eliminate those and come up with a final structure. Step 4 then is to get a final shape for your molecular polyatomic ion by looking at your preliminary shape and removing any parts that contain lone pairs of electrons. So again, we don't have this here. We'll see it in the next one. So this would be then our final answer. The dot structure, the number of electron domains, and then our 3-dimensional structure. Let's try water. So we know that the dot structure for water, recall from class, looks something like this. Step 2, we count the number of electron domains around the central atom. So here we have our bonding pairs, so that would be 2, but we also have these lone pairs that are on the oxygen. So there are actually 4 electron domains around the water molecule. So there are 4 sets of things that are trying to get away from each other or repel each other, or that they repel each other and are trying to move away from each other. Step 3, the 4 electron domains is going to give us a preliminary shape of a tetrahedral. So we'll go ahead and draw the oxygen here, And we'll have one thing going up, one going down to the right. So those are both in the plane of the board. We'll have one that's coming out of the plane of the board and one that's going back behind the board. So this would be our tetrahedral preliminary shape. Now, when we go to place the things in each of these spaces, for a tetrahedral, it really doesn't matter where we put the hydrogens and the lone pairs. So I'm going to go ahead and put the hydrogens here and here, so they're in the plane of the paper with the oxygen. And then I'll take my lone pairs and put them at the end of the bonds. Well, they aren't bonds. I'll put them at the end of the locations that are coming out of the board and back into the board. Step 4, to get a final shape, we're going to have to eliminate the part that includes the lone pairs. So in essence, what I'm going to do is kind of erase these two positions right here. And so I would get a final shape that would look like this. Now, the angle here, because we have just electrons over on the other side, that angle actually is going to get scrunched in a little bit. So that angle there is going to end up being 104.5 degrees. The exact amount probably isn't going to be all that significant for us at this point, but we do want to know that the lone pairs that are located on the other side of the oxygen are pushing those in just a little bit so that they're a little bit more scrunched in. Now, the name here would be called bent or angular. So you'd have a name to go along with that also. Here's a summary of all the different shapes up through 4 electron domains. So you can see that we have our two electron pairs in which both are bonds, and we get our linear molecule. 3 electron pairs where all 3 are bonding pairs, and so we get our trigonoplanar molecule. If we have 4 electron pairs and all of them are bonding, we end up with a tetrahedral, and the preliminary shape is the final shape. If we have 4 electron domains, but only 3 of them are bonding, so there's one that's a lone pair, we end up with a preliminary shape that's a tetrahedral, but then a final shape that's a trigonal pyramidal. And so at least one of the ones that you do for homework tonight should have that type of shape. If you have 4 electron domains and only 2 of them are bonding, you have a tetrahedral preliminary shape, but then we have a bent or V-shaped, just like water. So hopefully this will help you do some of these structures. We'll obviously practice them more in class as we go further with these.